All right, let's get right into it. For years, anyone building a really big, large-scale database has been stuck with this frustrating choice, a fundamental compromise that's been holding back what's possible. Today, we're going to look at a system called Chardonnay that says it has finally cured that dilemma.
And here is that choice boiled down. Do you want your database to be blazing fast? Or do you want it to be perfectly 100% safe and consistent with your data? You see, for the biggest, most demanding applications out there, getting both has felt, well, pretty much impossible. And it's been a massive headache for developers just trying to build things that are both reliable and high performance. So let's really break this down. We're calling it the distributed database dilemma. And it's all about this long-standing tug of war between raw speed on one side and guaranteed data safety on the other. Historically, you had two options on the menu, and frankly, neither was great. On the left, you've got the slow and safe approach. This uses a protocol called two-phase commit, you'll hear it called 2PC, to make absolutely sure that a transaction is handled correctly across multiple machines. It's the gold standard for safety for sure, but it has a reputation for being an absolute snail. Then on the right, you've got the fast and limited crowd. These systems ditch 2PC to get that speed, but there's always a catch, right? You either have to sacrifice data safety, put handcuffs on your developers, or you just can't scale the system out. You're always giving something up. But here is the first major plot twist in this story. That old villain we just talked about, the slow 2PC protocol, turns out it's not really the villain anymore. Thanks to insanely fast modern data center networks and new kinds of storage, the protocol itself is no longer slow. We're talking microseconds. The thing that used to be the main bottleneck has pretty much vanished. So you fix one problem, and what happens? You uncover a new one. With 2PC suddenly being super fast, a totally different and honestly a much more subtle performance killer was finally exposed. And that new killer has a name, the contention footprint. Now, the definition is right there, but here's a simple way to think about it. Imagine you go to the grocery store to get a can of soup, but to do that, you have to lock the entire aisle. No one else can come in and grab anything until you are completely done. The total amount of time you keep that aisle locked, that's your contention footprint. And in the database world, that's what was causing the massive traffic jams. This chart is the big aha moment. Just look at this. Bar number 1, baseline slow. That's the old world. You can see that big chunk of time was the slow protocol, 2PC. Now look at the middle bar. The 2PC part is tiny now because it's fast. But the overall time is still huge. Why? Because this new monster was revealed. The time spent just reading data from slow storage while the locks are held. And then, look at Chardonnay on the right. It's tiny. They figured out how to shrink both parts of the problem down to almost nothing. So how in the world did they pull that off? Well, this brings us to Chardonnay's secret weapon. It's an incredibly clever technique they call the dry run, and it's designed to do one thing: conquer that contention footprint. So here's a quick peek under the hood at the system's architecture. You've got the client kicking things off, talking to a service where the data lives, and a couple of other components to keep everything in sync. The real magic, though, isn't in the boxes and arrows themselves, but in the process, the flow of how they all work together. And here it is, the dry run, explained in 3 simple steps. First up, preview. Chardonnay does a practice run of the transaction. The key thing here is it's totally lock-free. It's just peeking at what the transaction is trying to do to see what data it's going to need. Step 2, prefetch. Now that it knows exactly what data it needs, it goes and grabs all of it from slow storage and loads it up into super fast memory. And then, and only then, does step 3 happen: execute. This is when it runs the real transaction and actually takes out the locks. But because all the slow data reading work is already done, this step is lightning fast. The locks are held for the absolute minimum amount of time possible. It's so elegant. Now, you might be wondering, okay, that's fast, but what did they have to give up in terms of safety? And the answer is nothing. Absolutely nothing. Chardonnay provides strict serializability, which is the gold standard of data consistency. It's a guarantee that even with millions of things happening at once, the outcome is the same as if every single transaction executed one by one in a perfect orderly line. Fast and safe. But that's not all. You see, this dry run trick is kind of the gift that keeps on giving. It doesn't just crush the contention footprint. It also solves another classic and incredibly frustrating problem in distributed databases. And we are talking about deadlocks. A deadlock is exactly what it sounds like, a digital gridlock. Imagine 2 transactions, A and B.
Transaction A has a lock on a resource that B needs, but B has a lock on a resource that A needs. They're both stuck, waiting for the other one to move. They can't. They're deadlocked. And usually, the only way out is for the system to just kill one of them and have it start over. It's incredibly wasteful.
So how does Chardonnay fix this? Well, remember, because of that dry run, it knows ahead of time every single piece of data the transaction is going to touch. So it can be really smart about it. It enforces one simple rule. You must always acquire your locks in a specific, predefined order, say alphabetically by key name. By enforcing this strict ordering, that circular I'm waiting for you, you're waiting for me situation becomes structurally impossible. It just can't happen. And just like that, the problem of deadlocks is basically gone.
Okay, this all sounds amazing in theory. It's fast, it's safe, it avoids deadlocks, but does it actually hold up under pressure? Let's look at the numbers and put it to the test.
So first, you take a traditional system and you put it under high contention. That means tons of transactions are all trying to access the same few popular pieces of data. What happens? Its performance just falls off a cliff. Throughput drops by a staggering 85%. It just can't handle the pressure. Now, you run the exact same high-stress test on Chardonnay. What happens? Throughput drops by only 15%. That isn't just better, it's a completely different class of performance. It shows just how resilient this design really is. This chart just says it all. As you crank up the pressure, as you increase that data contention, look at what happens. The baseline system it gives up. The throughput tanks. But Chardonnay, it just keeps on trucking. It maintains its high performance right when you need it the most. The difference is night and day.
So we're going to end on this quote from the paper's authors because it points to something way bigger than just one database. What they're saying is that because our networks are so mind-bogglingly fast now, the old rules we used for designing computer systems are changing. The line between designing a system for one giant computer and designing one for a whole fleet of computers is starting to blur. Chardonnay's success isn't just a cool new database trick. It's a signal that a lot of our old assumptions about what is and isn't possible are ready to be thrown out. Which leaves us with a pretty fascinating thought. What other impossibilities are now possible?